we'll calculate the total energy for an orbit. We're going to assume that the central object is much more massive than the objects in orbit around it, and there are no third big objects to be considered. So situation is the Venus orbiting the Sun, or Earth orbiting the Sun, Mars orbiting the Sun, Hubble Telescope orbiting the Earth. We'll ignore the Sun's interaction there. But how could we write out the expression for the total energy? Well, the total energy is equal to the kinetic energy, 1/2 mv squared, plus the potential energy. And the potential energy actually is defined to have a minus sign in it. The potential energy is negative. So the potential is negative until we get to infinitely far apart, then it's zero. But the way the traditional definition of gravitational potential energy is set up, the potential energies are negative. So let's take what happens when we look at Venus in its orbit around the Sun as to what the total energy is. So the total energy, I'm going to go ahead and drop in numbers I just looked up in an astronomy book and did a few calculations. I'm going to assume a circular orbit, but total energy 1/2. The mass of Venus is 4.868 times 10 to the 24th kilograms. It's a little bit smaller than the Earth. The speed in its orbit, assumed a circular orbit, is 35 times 10 to the 3rd meters per second. And we have to square that. And then I have to put in the calculation for the potential energy. This is just the kinetic energy. So for the potential energy, we've got 6.67 times 10 to the minus 11, the gravitational constant. And we have the mass of the Sun, 1.99 times 10 to the 30th kilograms. That's for the Sun. And then we need again the mass of Venus. So 4.868 times 10 to the 24th kilograms. And then assuming Venus has a circular orbit, we get 108.2 times 10 to the 9th meters as the separation of the two objects. So we go ahead and do the calculation here. For the kinetic energy, 1/2 mass and velocity squared, it's 2.982 times 10 to the 33rd joules. Then a minus sign, the potential energy is negative. And this, you should work this out on your own, but it's 5.972 times 10 to the 33rd, and that's a negative. So our total energy is negative 2.99 times 10 to the 33rd joules. And we'll just let that percolate in your mind a little bit. As far as I know, I've not made an error. The total energy is negative. I expected that to be a negative number. So for an object in orbit. What about the Earth? Well, same style of calculation. Kinetic energy and the potential energy are added up. Again, the potential energy will be negative. But for the Earth, we have 1/2. The mass of the Earth, 5.98 times 10 to the 24th kilograms. And assuming a circular orbit for the Earth, we get, I'm seeing a discrepancy here, but 29.8 times 10 to the 3rd. Hope I've got that correct. It seems reasonable. The inner planets are faster than the outer planets, so just have something written down on the notes that I'm looking at, written down a little incorrectly. But no matter, we continue. Then the potential energy, mass of the Sun again, kilograms, mass of the Earth, 5.98 times 10 to the 24th. And for our circular orbit for the Earth, 1.496 times 10 to the 11th meters. This is 1.08 times 10 to the 11th, so 1.496 times 10 to the 11th. The Earth is further away. You do this calculation, the kinetic energy, 2.65 times 10 to the 33rd joules. The potential energy, negative 5.31 times 10 to the 33rd joules. The overall total energy, negative 2.66 times 10 to the 33rd joules. Let's try Mars. Maybe we'll get a different result for Mars. So for Mars, and again, kinetic energy and potential energy. Mass of Mars is considerably smaller, 6.418 times 10 to the 23rd kilograms. We're further out in the solar system, so our velocity is smaller. And repeat these numbers for G, the mass of the Sun, and repeat the mass of Mars here. Almost running out of paper. But 6.418 times 10 to the 23rd kilograms. And again, putting in the distance to Mars from the Sun. 6.927 times, oops, sorry, on the wrong line here. 2.279 times 10 to the 11th meters. So the kinetic energy for Mars, 1.87 times 10 to the 32 joules. The potential energy, minus 3.74 times 10 to the 32nd joules. And our total energy, well, again, negative. And 1.87 times 10 to the 32 joules. Another negative there. Negative, negative, negative. This is good. When the energy is less than 0, we have a bound orbit. When the total energy is less than 0, we have a bound orbit. And certainly Venus, Earth, and Mars are bound to the Sun. What about the Hubble Telescope? So again, I'm going to ignore the Sun here, but doing the calculation for the Hubble Telescope, and again, I've looked up some numbers about the mass of the Hubble Telescope when it was launched, at least. And from its orbit and the time to go around the Earth, we can calculate the speed, assuming a circular orbit. So making some assumptions here, but again, total energy, 1/2 the mass of the Hubble Telescope, 1.1 times 10 to the 4th. Hubble Telescope's a lot less massive than the Earth. And then its speed in orbit, 7.64 times 10 to the 3rd squared. This is ignoring the Hubble Telescope's motion around the Sun. This is just doing the orbit around the Earth. And then, again, the gravitational calculation. Mass of the Earth now is needed, 5.98 times 10 to the 24th. The mass of the Hubble Telescope, 1.11 times 10 to the 4th kilograms. And here's where that number was that I was almost put in, 6.927 times 10 to the 6 meters. And if you look up the information about the orbit of the Hubble Telescope, you'll find that it's some number of kilometers above the surface of the Earth. Don't forget to add in the radius of the Earth. This our number is from the center of the Hubble Telescope to the center of the Earth, not the distance of the Hubble Telescope to the surface of the Earth, not the altitude, but center to center. So for the kinetic energy, 3.24 times 10 to the 11th joules. For the potential energy, negative 6.39 times 10 to the 11th. The total energy, and going off the screen here just a little bit, is minus 3.16 times 10 to the 11th joules. Again, negative. The Hubble telescope is not leaving Earth orbit, it's bound to the Earth. So total energy for an orbit, and this is true for atoms as well in the future when you study atoms. The energy of the total energy for the electron in an atom is negative. That's bound. To ionize an atom, you have to supply enough energy to make that energy positive. If we were going to ionize Venus from the Sun, we would have to supply Venus with 2.99 times 10 to the 33rd joules of energy to get Venus to escape from the Sun. There are spacecraft, 5 spacecraft that have enough energy to leave our solar system. The 2 Voyager, the 2 Pioneer, and the New Horizons spacecraft that flew by Pluto in 2015. So practice with these, and maybe play back the video and pause from section to section. Make sure you're doing these calculations on your own so you're familiar with how to calculate kinetic energy and potential energy. And know the concept. When the total energy is negative, the object is bound in an orbit. It's not going to leave its object. So ask your instructor some questions on this.